In this lecture, we are going through a checklist that is used to classify a factor as either fixed or random. I compiled the checklist from a large number of sources, including the books by Natter and Montgomery that I used as a PhD student of statistics. These books are great in many respects, but they have a rather shallow coverage of the distinction between fixed and random factors. Still, I'm going to refer to these books quite a bit because they have useful information such as ANOVA tables and expected mean squares for different designs. Our professor also showed us briefly how to use Hasse diagram to choose the correct denominator for the f-statistic in a mixed model, and that was it. Another reason why I graduated with little knowledge of the subject is that back then my main interest was in quantitative finance, and I didn't know of any applications of random effects in that area. Likewise, understanding random effects is far easier if one is familiar with experimental design. But for quantitative finance research, experimental design appears useless because virtually all of the financial data sets are observational. Now, let's get to the first item in the checklist. Suppose a factor has a finite number of levels, all of which are used in the current study, and all of which would be used in a repeat study. In that case, the factor is fixed, otherwise it's random. Here's a slightly modified example from the book of Natter. A large company has 500 personnel officers. An officer's task is to interview job candidates and assign a rating to each candidate on a scale of 1 to 100. 5 officers are selected at random, and each officer interviews its own set of 10 candidates. As a result, we have a model with one officer factor with 5 levels, and 50 observed ratings represent the response. The officer factor is considered random because the 5 officers represent a large population of officers, and if we were to repeat the study, most likely a different set of 5 officers would be selected. Now imagine that the company is much smaller and it only has 5 personnel officers, all of whom are used for the study. If we were to repeat the study, the very same officers would be chosen. So in that case, the officer factor should be treated as fixed. Another source rephrases the rule as follows. If the factor is fixed, we won't see more levels of the factor if we collect more data. This distinction is less clear because, even in the simple officer example, there are at least 2 ways to collect more data. First, we use the same 5 officers as in the original study and have them interview more candidates. Second, we can add more officers to the study. In the first case, no new officers will be observed, so we can erroneously conclude that the factor is fixed. Further, these guidelines suggest that as the total count of officers in the company goes down, it becomes more and more justifiable to label the officer factor as fixed. For instance, if the total count is 7 instead of 500, and 5 people are selected at random, then it's quite possible that in a repeat study, the same or almost the same 5 officers would be selected. So it's far more reasonable to treat the officer factor as fixed. This goes to show that the distinction between fixed and random is on a continuous rather than binary scale. It would be nice to have a rule of thumb for when the ratio of sample size to the population size becomes so large that it's okay to treat the factor as fixed. But the Book of Netter never discusses the topic in such depth. Let's continue with the checklist. The next item is not helpful, and here's why. Suppose the study contains a nuisance factor that is truly fixed. If we mislabel it as random, then it might affect the p-values for the factors that are of interest in the study, and we might end up with incorrect p-values. In other words, it is often appropriate to treat nuisance, blocking, or control factors as random, but nuisance is not equivalent to random. Next, we can ask ourselves if we are interested in estimating or comparing the mean response for each factor level, such as each individual personnel officer. If yes, the officer factor should be fixed. If we are only interested in learning what proportion of response variance is due to the officer factor as a whole, then the factor is random. This rule is a refined version of the previous one, but it has the same flaw. If there is a fixed nuisance factor in which we have no interest whatsoever, we can mislabel it as random, which can affect the p-values for the factors we are interested in. Besides, these rules create an impression that the very same dataset and factor can be treated differently depending on some subjective direction of interest that can change from one researcher to the next. Finally, a different source points out that even when the factor is random, the researcher can still be interested in looking at the so-called realized values of random effects. Consider the model statement for the personnel study. I is the officer index from 1 to 5. J is the candidate index from 1 to 10. Yij is the assigned rating. Mu is the mean response, and epsilon ij is the random error term. The value pi is the effect of ith officer. Technically, treating the officer factor as random means that all pi's are drawn from normal distribution with zero mean and certain variance. It's possible to obtain a predicted value and prediction interval for the realized value of each pi. In other words, it is still quite acceptable and technically feasible to exercise interest in individual officers. The next item on the list is quite simple, but the simplicity is taken too far because the sources do not elaborate on why this rule is valid. Based on what I know, the first part is true indeed. There is no theoretical or practical way to label a quantitative factor as random. Note how this rule is at odds with one that states that nuisance or control terms should be random. It's quite possible to have a quantitative control factor, but there is no way to include it as random in the model. As for nested effects, we'll focus more on them later. For now, it's enough to say that when a nested design is first introduced in the book of Netter, all the factors are considered fixed, which is at odds with this rule and is rather confusing. This item describes how the inference changes when we switch from fixed to random. It makes me think of two questions. First, in either case, our inference is based on a rather small sample from a large population. That's the essence of statistics as a science. Given that limited sample, how come it's enough to just change the factor label from fixed to random to make the inference apply to the entire population? What's the magic trick? Second, consider a simple linear regression with one single quantitative factor. That factor is fixed because, as you know by now, all quantitative factors are fixed. Nevertheless, the inference applies not only to the levels of predictor observed in the dataset, but to the entire population from which the sample is drawn. We know that it's best to apply the trained model over the same range of predictor that was used for training, but that recommendation is practical, not theoretical. In theory, the inference applies to the entire population of predictor levels. Otherwise, the model would be useless because it would amount to a peculiar form of descriptive statistic that applies only to the specific sample. We see that when the model contains a fixed quantitative predictor, the inference applies to the population. But if the predictor is categorical, that is not the case, unless we denote the predictor as random. It's not clear why this discrepancy takes place, why a fixed categorical factor cannot behave in the same way as a fixed quantitative factor. One visible distinction between fixed and mixed models is that for a mixed model, the variance covariance matrix of response vector is not diagonal. In the personnel officer example, the matrix consists of 5 blocks because observations coming from a given officer are correlated. Therefore, one could say that a random factor allows us to model correlated observations or clustered data. However, if you look at the model equation, you'll see that observations coming from the same officer share a common officer effect, pi, and that is true regardless of whether the effect is fixed or random. Even if it is fixed, the model still implies that observations coming from the same officer are more similar to each other than the observations coming from different officers. Therefore, it's not obvious why we need random effects to model correlated or clustered data. The last point describes a practically important consideration, because one might not be able to include a factor as random, even if one wanted to. Insufficient amount of data is an issue regardless of the model, but in mixed models it's more pronounced for computational reasons. In a fixed case, one is very likely to use a robust ordinary least squares that converges in one step and rarely fails. For a mixed version of the model, estimation methods are far more unstable, and one can end up with a convergence failure or a non-positive variance estimate. As a result, one might have to fit the model separately for each level of the random factor, which underscores that the inference cannot be generalized to the population of factor levels because of small sample size. To fit a mixed model successfully, one must have decent replication at more than one level. In the personnel example, one needs to have both lots of candidates and lots of officers to be able to afford to treat the officer factor as random. As you can see, the difference between the two types of factors is not straightforward. In the next lecture, we are going to consider some corner cases where the distinction is especially fine.